Okay, hello everyone. Welcome to the lecture. Uh, just a quick recap on what we were trying to cover or what we were talking about in the last meeting. So we were talking about different architectures and why we were looking at different architectures because our main question was like uh, how can we increase the computing power of uh, how we can increase the computing power of a given system. And what we talked about was like the power is actually measured by, let's say, for our purposes, the measure is like how many processes we can run on a given computer at a time. So if we have a single CPU, we said, okay, we can run only one process at a time or one program at a time. So, but the problem with this approach is that since we can run only one at a time, so it is not a realistic architecture for modern computing needs because the modern systems we need high throughput. Okay. And that is the point where we had to stop. So before we start our today's lecture, are there any questions which you guys would like to ask? Any comments? No? Okay. If no, then in that case, Uh, so first we had a look at single processor system where we have a single processor, and within the single processor chip, we have a single CPU having a single core, right? And the core we said is the collection of components, including execution pipeline and register files, right? But the issue with this uh, kind of system is like, since we have a single core, we can run only a single process at a time, a single program at a time, and which means that it has very low throughput. So we want to increase the throughput. So to increase the throughput, then the straightforward solution is like logical solution is that we can basically have multiple processor chips in a single machine. So now this time we have a computer where we have two different processor chips. Each one of them have their own CPU, CPU 0 and CPU 1, and which basically mean that we still have a single core on one processor, and the both processors they share the memory, right? And remember, I guess we also covered this slide. So we said that there are two kind of multiprocessor systems. In this particular figure, we have only two processors, but we can have more than two. So asymmetric multiprocessors are those systems where each process is designed are capable of executing a special task. For example, one processor can execute only user level code and the other can execute only system level code, or one can execute, let's say, all other instructions but not the floating point instructions, and the second processor is designed only for executing the floating point instructions. On the other hand, symmetric multiprocessing are those systems where each processor, again, we have multiple processors, but each processor can perform all tasks. There is no, how to say, categorization that a given processor can perform only certain set of tasks and not the other set of tasks.
Basically, all the processors are able to do the same thing then.
Sorry, say again.
Or for the asymmetrical, the processors aren't able to do the same thing. With symmetrical, they are able to do the same
Yeah,
things,
yeah,
like
that's
same
correct.
capabilities.
Yeah,
Okay.
that's correct. That's correct. So if in such a system, if we want to measure the speed up, so it's a straightforward process. It is just like, for example, if I want to do uh, a given, for example, let's say if I want to uh, wash 10 dishes and I have only one person who is washing the dishes, then, and let's say each dish takes 1 minute, so the job will be completed in 10 minutes, right? But now if I compare it with the situation where I have uh, 10 persons or 10 washers who are working on the dishes, and each one of them is washing one dish, so then it's mean that all the 10 dishes, they will be cleaned in 1 minute, right? So what will be the speed up? So speed, how can I calculate the speed up? the time it takes to clean the 10 dishes in first situation, where it was 10 minutes, and divided by the time it takes to complete the dishes or clean the dishes in the second situation. So which is 1 minute. So 10 divided by 1 is 10. So which is equal to the number of the extra number of the washers or number of the cleaners I have in the second situation, right? So you can simply use the same analogy even when you want to calculate the speed up of a multiprocessor system as compared to a single processor system. So if you have one processor working on P processes, P number of processes, and each process takes T unit of time, then it's mean that single processor will complete those P processes in P times T unit of time, right? Let me. So it will complete those P processes in P times T amount of time, right? But now if I have N processors, and N is the same as the number of processes, so, and then each processor can run its own process, then it's mean that all of the P number of processes will be completed in T time, right? So speed up it is how long it takes to complete the P processes by one processor, and how long it takes to complete the same number of processes when we use uh, N number of processors. So we simply divide the time and we get P, so which is equal to N. So basically what we are trying to say is, like, if we have N processors, then we can have the speed up of N times, just like in that uh, washer example. Like if we have 10 persons cleaning the dishes, then we can have 10 times of the speed up, 10 times speed up, right? However, in practical situation, yes, we still get the speed up, but it is not as high as number of the processors we have in a multiprocessor system. Why? Because these processors which are on the same machine, on the same computer, yes, we have separate processors and each one of them can run a process, but when you run a process, you need several resources. CPU is only one of those resources. So, but there are other resources which are also needed for the execution of a process. For example, memory, right? For example, using the uh, for example, accessing the memory, or using the main memory bus, and other kind of resources. So let's say if we keep this thing simple and we say that a process needs only two resources to execute, one is CPU time and the other is main memory accesses. Now, if I have two processes, each one of them have their own CPUs, but they are sharing the main memory. They don't have separate memories, right? So which means that main memory becomes a bottleneck, or they are competing for the main memory. So if one of them gets the access to the main memory, the other must wait, right? And so they must take turns, which actually slows it down, right? So that's why your actual speed up is not N times, it is less than N, because due to competition for shared resources. Also, if there is a situation where we have, let's say, two or more than two processes and they are cooperating with each other to complete a task, they may need to communicate with each other, and they may need to communicate, then they may need to access the same location in memory, but they need to ensure the correctness. For example, the data written by process running on CPU 0 is then read by the process running on CPU 1, right? So it's mean that process running on CPU 1 must read it after the data is written by the process running on CPU 0. So which means that we need to enforce ordering, for which we need extra mechanisms to enforce the ordering or ordered access to the memory, right? So it also incurs extra overhead, not only communication, but also how to say orchestrating accesses to the memory. So because of these factors, our actual speed up is less than N. So in this kind of situation, or in this kind of system where we have multiple processors on a single machine, there can be situation when a single processor may become overloaded. So for example, let's say we have only two processors and we need to run four different processes or four different programs, right? So there can be a situation where, let's say, we need to run four different processes and we need to run four different programs, right? So there can be a situation where, let's say, we have only two processors and we need to run four different processes or four different programs, right? So it, there can be a situation where, let's say, we need to run four different processes and we need to run four different programs, right? So uh, CPU 0 is busy all the time, and like it is continuously executing one of those processes, while CPU 1 is staying idle, or is it free for most of the time, right? But we don't want to end up in that kind of situation, because that is like underutilization or wastage of resources. We want to balance the load in such a way that we keep both CPU 0 and CPU 1 occupied, right? No, none of them is free. If there is work to do, none of them should be sitting idle, right? So for that, we need to look at how the processes are scheduled on CPU, right? This is known as CPU scheduling, and we will talk about that in week 6, 7, and 8. Uh, Also, when you have two or more processes running on different processors, they may need to cooperate with each other to complete a task. And as I like briefly explained in the in the previous slide, they may need to have uh, ordered accesses to the memory, to the shared data, which mean that their accesses need to be synchronized with each other. And we will talk about the synchronization mechanism in week 8 and 9, right? But these are why I am explaining this, because these are the implications of having a system where you can run multiple processes on different processors at the same time, right? But then you need to take care of special problem or challenges. Also, uh, if you have multiple processes, there may be situations can arise there where these processes need to communicate with each other. And if they need to communicate with each other, for example, in this particular setting, then it means how they can communicate. So if they can like communicate, they must like communicate through memory, because main memory is the shared resource, right? So for example, let's say the process A running on, let's say, processor 0, and process B is running on processor 1. So let's say if A wants to send some data to B, it will first put that data in memory. Let's say that data is X, and then B will read it from the memory. But then it's mean that data crosses the chip boundaries, right? Processor 0 is a separate chip, processor B is a separate chip, right? Uh, So, and memory is also a separate chip. So there is a communication uh, between two different chips. Our communication is crossing the boundary. Always remember that when signals travel between two chips, it is much more expensive in terms of latency, as compared to the case when signals travel or information is exchanged between two components on the same chip. So as a result, if two processes need to share data and they need to perform the inter-process communication, it is expensive in this kind of architecture. So if we look at the positives of this approach, then the positive thing is that we can run multiple processes simultaneously, and per processor, which increases our throughput. That is a good thing. However, the problem is that in this approach we have in this design, we have bus as a bottleneck. Because why? Because bus is the shared resource, and anyone who wants to access the main memory, or even like if two processes need to communicate, or two processes need to communicate with each other, they must share the memory. So bus becomes a bottleneck. Also, here what we are doing is that if we compare this with a single processor system, so what is different? The different thing is that we are replicating the processors. In previous single processor design, we had a single processor connected with the main memory. Now we are replicating the processors, like it can be 2, 4, 8, and so on, right? But processors are larger in size as compared to the cores. Remember, what is core? Core is just an execution unit and the set of registers. So core is actually a component or a subset of the processor itself. So since a processor is larger in space, or larger in size, it consumes more power. So this is like a thumb rule, like whenever there is a piece of hardware which has larger area on the chip, then it is expected to have typically more power consumption as compared to a component which takes smaller area on the chip, right? Also, since memory is a shared resource, so we need to have some mechanism to ensure orderly memory accesses to ensure the correctness of data in the memory. So these are the challenges, or these are how to say negatives of multiprocessor design. But let's say that our target is that we still want to increase, we still want to achieve higher throughput, higher than what our current multiprocessor systems are offering. We want to achieve low communication latency, and we want to achieve low power consumption. So if that is our target, what changes we should make into this approach so that we can achieve more throughput, low communication latency, and low power consumption? Anyone who want to answer? If you want to answer, you can simply send me a text chat box. You can unmute yourself.
Can you repeat the question, please?
Okay, let's say that you see the multiprocessor system sample design here in this slide, right? Now we talked about his pros and cons. Pros is like the positive thing is like we can run multiple processes and hence we can achieve the higher throughput. But the negative things are that our memory and the bus, they become a bottleneck because they are the shared resource, one thing. Processors are larger in size as compared to the cores. Since they are larger, they also consume more power. So like if I keep increasing the, let's say, number of processors, and I will add, let's say, from 2 to 4 and then to 8, then it's mean that I will have more processors and they will consume more power, and my system will be like heating up quickly, or then I will need a mechanism to cooling mechanism, right? Also, the memory is a bottle. I need to make sure that all the accesses to memory are performed in an orderly fashion, so that data correctness is ensured. So these are the problems with this design. So given that, let's say my target is that still I want to do a design, or I want to find a solution where I can achieve more throughput, which basically mean that I can run more processes in a given amount of time, but without increasing the communication latency and without incurring more power consumption. One way, for example, to increase the throughput is like I increase number of processors from 2 to 4. Now I will be able to run more processes at the same amount at a given time, right? But then it will also increase my power consumption. And if those processes are communicating with each other, it will increase my communication latency, right? So what is the solution? What changes I can make in this approach or in this figure so that I can still have high throughput but incur relatively low communication latency and relatively low power consumption relative to the case where I increase the number of processors from 2 to 4. Now, anyone who want to respond?
Is it related to the idea of like running multiple threads at once, where kind of you have multiple tasks going simultaneously to try and be more efficient, or?
Yeah, you brought up the idea, notion of thread. Yeah, but at one level you are correct, but we need to discuss this in more detail, right?
Right, but there's a
I
bit
will
more to it.
explain. Yeah.
Okay.
Yeah, I will explain. And someone said, could you add an extra bus connection directly from processor 0 to 1? So, okay, the bus connection between processor 0 and 1 is like, let's say if there is a bus connection, but there is no memory. So then, okay, if you are saying, okay, let's keep the bus connection between main memory and processor 0, or if you want me to draw, I can do it. So are you saying, if you are saying we can keep this connection, we can keep this connection, and then we can do a connection here, right? So, okay, if you are saying that, now let's say that I have some data A in this. So A in cache of CPU actually came from memory. So it was moved from memory into cache of CPU 0. And then it was also copied here because processor B also needed it, right? Now, if you are saying like, okay, we can do direct communication so that we don't need to go to the memory, it doesn't solve the problem. Why? One thing first, this is still crossing the chip boundary. So still we will be paying extra communication latency. Our power consumption will still be same because still we have two processors here, right? And the only difference will come when CPU 0, when process 0 or process A need to talk with process B, but then the data which is in their cache, it can become obsolete. Obsolete, for example, let's say process A changes A to A complement, but B is still copying A, and in main memory it is still A. So there is like, this is valid copy, this is invalid. This is invalid. So if process A directly provides A complement or A bar to the process B and it becomes A bar, now it is not same, it is not synchronized with memory, right? So there are other challenges, but it doesn't solve our problem of more throughput, more low communication latency and low power computing. It actually makes our problem worse. Okay. So the solution is okay. So the solution is that we, instead of having multiprocessor systems, we have multi-core multiprocessor systems. What does that mean? So just look at this figure. So again, we have same thing. We have two processors now, but within each processor, we have two cores. Like in processor 0, we have core 0 and core 1. And in processor 1, we have core 2 and core 3. So in total, in the system, we have 4 different cores, right? And the other thing is like the core, it has its execution unit, its registers, and L1 cache, private L1 cache. Each core has its own private L1 cache, and L2 cache is shared between two cores in the same processor, right? And same is the case here. The two cores in processor 1, they have their own private L1 cache and they have shared L2 cache. And then the memory is in a different chip. Remember, the important thing is that these two cores are on the same chip and these two cores are on the same chip, right? And memory is a shared resource now. So basically what we are saying is that replicate not big processor but small cores. Since cores are smaller in size, why? Because they are a subset of a processor. They have only registers and they have L1 cache. So what we say, like for example, compare this with the situation where instead of having 4 cores, you have 4 processors. Like just if we go back to here, right? If we go back here, what will happen? You will have registers, you will have caches L1, L2 in each processor. You will have all other components in each processors, which we have not shown in this figure, like for example, predictors, prefetchers, TLBs, and other components of which we are not going to talk about in this course because this course is not about computer architecture. So we will have all those components in each of the chip, right? So if you simply replicate, so you are making 4 copies of everything. Now compare it with this one. Here, you have 4 cores and you are replicating only registers, L1 cache and execution unit, not other things, right? And even L2 cache is not replicated 4 times. It is replicated only 2 times because 2 cores are sharing the L2 cache, okay? So it's mean that you are replicating smaller amount of components as compared to the case where if you have replicated this processor 4 times, right? So since you are replicating lesser number of components, it's mean that you will definitely consume less power as compared to the case where you had replicated everything 4 times. So replicate not big processor but small cores, and as a result, you can achieve the lower power consumption. Okay. In the previous example, does the CPU still have the 4 cores but they are not used correctly, or the new example just shows that each CPU should have more computing power by using more cores? No, in the previous example, each processor has only a single core. Here, you are talking about this one, right? So here, each processor 0 has single CPU, and within the CPU, it has only single core. So this has only core 0, and here processor 1 has only one core, one CPU, and which has only one core. Remember, core is just a subcomponent, a subset of the components of CPU. If you want, I can go quickly back to the first slide here. So these are the processor components, let's say, execution pipeline, register file, caches, TLB, prefetches. So processor, then this thing in the block is a single core, okay? Or maybe like you can also optionally include cache as L1 cache as a part of the core and L2 as the part of the CPU or processor. I hope it answers your question. If not, let me know. Okay. So each core appears as a single processor to now here we have 4 cores in this figure. The good thing is that from the perspective of the operating system, each of these cores actually are logically a single processor. So which basically mean that OS needs for an OS, it is enough to have a core to run a process. So then it means that the OS can run process A on core 0, process B on core 1, process C on core 2, and process D on core 3. Okay. So as a result, what happens that now we can run 4 different processes at the same time on this platform, right? Also, one other thing is that this is what one of your friends said, that what we can do is that we can divide a single process into multiple threads. We will talk about threads in more detail in upcoming lectures. We have complete like, I guess 1 or 2 weeks to talk about threads. So don't worry about that. But the basic idea is that if it is, this is, let's say you are an program, right? So normally what happens that your program starts from like one instruction and you keep executing it in the sequence, like first instruction, second, third, fourth, and so on, right? So this is very simple, our simplified explanation of thread. So when you divide an application into a process into threads, multiple threads, what you do is, let's say if I want to divide into 2 threads, I will do, okay, before going to that division into threads. So if I have single thread, threaded application, so what I will do is that in the program counter, and I assume you know what is program counter from your microcontroller course. So in the program counter, your program counters points to the first instruction in the executable instruction in the process. And then once the first instruction is executed, it points to the next one. After that, the next one, and so on, right? So instructions are executed in sequence. So this is like where you have single threaded application, right? Now to execute a single threaded application, you need an execution pipeline. So one pipeline, so actually this PC program counter feeds into this instruction, into this pipeline instructions one by one. So these are like, let's say these are stages of the pipeline, right? Now in multi-threaded application, what you do is you say, okay, I can divide my process into 2 equal sets, let's say. Again, I'm saying this is our simplified explanation. And you have two program counters, let's say PC1 and PC2. PC1 points to the first instruction in the first half, and it feeds into the pipeline 1, and you also have another pipeline. So, and PC2 points actually to the first instruction in the second half, and it directs these instructions into the second pipeline. And remember, these pipelines are inside different cores. So this is basically, this is core 0, let's say, and this is core 1, right? So this is idea of like, what you can do is that dividing a process into multiple threads, and then each thread run a separate core at the same time, right? As a result, what happens that your process completes faster as compared to the case where you had a single core or single processor system and where you had no threading. Okay, So hence you can achieve the higher throughput because each process can complete much quicker. You can also like extend it to the case, let's say instead of 2 threads to 4 threads and so on. Throughput in this context means output write. Throughput in the if you have, let's say, multiple processes running, so you can say, okay, you can define throughput as number of processes completed in a given in per unit time, right? And so if each of those processes are now multi-threaded and you can run them, you can run the threads on different cores at the same time, it's mean you can complete each of those processes relatively quicker, relatively faster as compared to the case where you had no multi-core system, right? So that's why your throughput increases. Did I answer the question or not? Okay, you're welcome. Does the bus have a higher throughput due to multiple cores, or do we still have the issue of a bottleneck to memory when transferring information? Okay. Someone asked, in this multi-core, multiprocessor system, does the bus have a higher throughput? So actually, he is asking that in this platform, is the memory bus still a bottleneck or not? Anyone who want to answer the question? Let me repeat. A friend of yours asked that in this platform, is memory still a bottleneck or not?
I think it is not.
Okay, can you please explain why not?
Yeah, because we already create a common cache for the two processor. So the information, if processor one send a message to processor two, so processor two is getting it from the L2 cache, not from the memory again.
Okay. Yeah, thank you. Thank you for your explanation. So yeah, definitely it depends upon the context and the situation. For example, the situation which the student has explained. So for example, let's say if you have two processes, A and B, running on core 0 and core 1. Now, let's say that the data they are operating on, the size of that data is small and it can be accommodated in L2 cache. So let's say first time the data is brought from memory into the L2 cache, and then all of the there is no need to go down to the memory once the data is loaded into L cache. So initially, yes, you need to traverse the memory, but not for the subsequent accesses, right? And if the communication is always like between A and B, then yeah, in this particular situation, since you are making much less accesses to the memory, so it will not be a problem. But then compare it with the situation where, let's say, the size of L2 cache is small and it cannot hold all the amount of data which is needed by A and B. So which basically means that data is brought from memory into the L2 cache, and when there is no more space, then older data is moved out of the L2 cache and put in the memory, and new data is again brought from memory into the L2 cache. So there are multiple accesses, right? Happening during the execution of the processes A and B, and same is the situation for, let's say, C and D. So which means like if there is a situation that A, B, and C and D are running processes which are memory intensive, which means they are making a lot of memory accesses, then memory will become a bottleneck. But if A, B, C, and D are, let's say, they are not memory intensive, but they are compute bound, which means they are doing a lot of computation and number of accesses made to memory are relatively small, then memory will not be a bottleneck. But again, we always need to compare oranges with oranges and apples with apples, right? So if we say if this approach or this platform has memory as a bottleneck, so it is for the case where both A and B are, let's say, one are competing from the memory, then memory becomes a bottleneck, right? So same here, if we compare it with the previous, we'll talk about the situation where A, B, C, and D are competing for the memory. So again, memory will be a bottleneck in this situation, right? We cannot compare with the previous situation, saying in the previous situation they are making lot of memory accesses, but here they are not making lot of nature of the processes such that they don't need lot of memory accesses. So memory is not a bottleneck, because that is the nature of the processes, that they are not making the accesses to the memory. But if I simply replace them with a different kind of processes which are memory intensive, so all of them will be competing with for the memory, and memory will become a bottleneck. Okay. Okay. I hope I answered the question. If not, let me know. Does each process run on one core, or each thread runs on one core? Okay, someone asks, does each process run on one core, or each thread runs on one core? Anyone who want to respond to that? I like this kind of like questions and answers. I am enjoying it personally, but it is slowing me down, but it's fine. Okay. Anyone who want to answer this question? Does each process run on one core, or each thread runs on the core, on one core? Okay, then let me try to answer. Actually, it is a core, it is a thread which runs on a core, not a process. Why? Because each process is basically consisted of one or more threads. Even if it is not a multi-threaded process, even then it has a single thread, right? Just like, for example, I explained here. So if you have an application, it is a process, it will have at least a single thread. Single thread is like your sequence of execution, right? It will have at least one sequence of execution starting from first instruction down to the last instruction, in like simplified example. Okay, so at least there will be single thread, and what we will have, program counter will point to the first instruction, and then it will increment the address so that it can point to the next instruction. So this is basically a thread which is running on a core. Okay. And as I said, application, if even they are not multi-threaded, yet they have at least one thread. So it's not right to say that a process runs on a core. Actually, it is a thread which runs on a core. I hope I answered the question. If not, let me know. Okay. Okay. So threads and concurrency, we will talk about that in week 4 and week 5. Okay. Let me escape this so that I can discard all these annotations and then start again. Okay, here each core has its own private L1 cache and shared L2 cache. Now, let's say I want to increase throughput even further. So now this, for example, this approach now allows me that I can run 4 threads, or let's say 4 single-threaded processes at the same time without incurring too much power consumption as compared to the case where I had 4 processors. And also by reducing the communication cost, because now L2 cache is say shared. So the all of the traffic which is like served or entertained by L2 cache, it doesn't need to cross the chip boundary. However, if traffic needs to cross the boundary and go to the memory, then it will be like more expensive. But definitely some portion, some percentage of the traffic will be entertained by the L2 cache, right? So let's say I want to now increase throughput even further, right? Then what can I do? Anyone who want to answer?
Maybe increasing the communication bandwidth.
Yeah, but you said increase the bandwidth, right?
Yes.
Memory bandwidth. But even if I increase memory bandwidth, I need more resources. Remember what resources we talked about? Basic 2 resources to run a process. One, CPU time, the core time, and the memory accesses. Even if I increase the memory bandwidth, it basically mean that now I can serve more data in the given amount of time, but I will still be serving the same data to the 4 processes, right? So how we measure the throughput? We measure the throughput by how many processes we can complete. But if we have only 4 processes which can read their data, the more data due to the high bandwidth, but we will be able to complete only 4 processes in given time. Yes, it will reduce the amount of time possibly in which you will be able to complete the processes, but it will not have a significant impact because the basic first ingredient or the first requirement is that you need to have a core to run a new process. So a friend of yours said that maybe we can possibly increase more cores, right? So yeah, that is one option, that we can keep adding more cores on a single processor. But if we do so, again, everything has implications. Nothing is like, there is no free lunch. So if we keep doing so, then it is possible that your L2 cache will become a bottleneck, right? Beyond a certain number of cores. How? Let me give you an example. Let's say that you have a 32 kilobyte L2 cache here. Let's say the size of this cache is 32 kilobyte, right? And let's say it is shared only among 2 cores, which are running 2 different processes, A and B, right? Now let's say the data set which is operated on by process A is 16 kilobyte, and the data set which is operated on by B is 16 kilobytes. So both of them are perfectly fit in 32 kilobyte cache, right? Now let's say if I increase the cores from 2 to 16 in a single processor. So I have A, B, C, like core 0, core 1 up to core 15 in processor 0. And all of them share the L2 cache, right? And let's say that all the processes, 16 processes running on them, each one have a data set of 16. Now, if you multiply 16 by 16, you can do the math. Their total data set will not be will be bigger than the size of the L2 cache or the capacity of the L2 cache, which basically mean that these processes running on A and B, they will have they will experience many more cache misses. So which basically mean that your L2 will become a bottleneck, right? Because it will be highly contested between A, B, and all other processes. Let's say process 0 to process 15, right? Could we add more caches or cache space? Yeah, we can, but again, there is no free lunch. So if you increase the cache size, one, it will increase your power consumption. Second, it will take more time for the cache circuitry to search for a particular data item within the cache, right? Which will basically mean that your time to access the data from the cache will increase, right? So you will have an increase in latency, you will have also an increase in power consumption, and also there is no limit. I mean, for example, let's say if you are saying I'm increasing the number of cores from 2 to 16, so I can also, which mean you are increasing it 8 times. So you say, okay, I can also increase the cache size 8 times from 32 to 8 times 32. Yes, but then one thing is like, again, as I said, there will be high power consumption. It will take more time to search the caches, and your processors core will become more expensive in terms of money. Okay. So which means that we need to think about some other solution which doesn't have these drawbacks. Okay. Maybe, as you said, private L2 core per core, shared larger L3 cache. So maybe what we can do is since we said that L2 can become a bottleneck, so what we can do is that we can have private L2 in each core, so which we can move it inside the core, in like replicate it inside, and then we have a larger L3 cache. But again, the same problem, since you are now replicating L2 cache into every core, you will increase the power consumption because you are increasing the size of the core. It will also become expensive, and then also there will be a point where L3 will become a bottleneck. Okay. So at this point, I just want to recall from one of the professors at KTH, Royal Institute of Technology in Sweden. Actually, he was our professor in during my master's program there, and he used to say that most of the times problems are not solved; they are transferred, like from one 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 point or one point in your design space to another point in your design space. So you just like if you optimize one point in design space, the other point is like not optimized. So same is the case here. Another option is like we can increase the number of cores per processors, right, to increase the throughput. So then we can increase the multi-core processors in the system, but then again your memory will become a bottleneck, just like it was a bottleneck in a multiprocessor system, right? So it looks like that we are hitting a wall, like either we increase the number of cores or we increase the size of the cache, or we add an extra cache, L3 cache, or we increase the number of processors. Every time everything will end up like creating problems in terms of more power consumption, or one or the other component will become a bottleneck. So maybe now we need to think in a different approach. And that different approach is non-uniform memory access. Okay. Now, what is that non-uniform memory access? Let me go to the next slide. Okay. So in non-uniform memory access platform, what the basic idea is that we have multiple CPUs like CPU 0, CPU 1, CPU 2, CPU 3. So where each CPU or group of CPU has its own local memory. For example, CPU has its own local memory 0, right? CPU U2 has its own local memory 2. Now, local memory is accessed through a small and fast memory bus. As compared to, so these local memories, you need to pay less latency or lower latency to accessing the data located on these local memories. However, if you okay, so and in the terminology of NUMA or non-uniform memory access, CPU, local memory, and your memory bus, local memory bus, they are collectively called a node. Now, the thing is like the pros of this approach is that if you have a process A, let's say running on memories, sorry, not on memory 0. I cannot undo it. I don't know how to undo it, but anyway, let's say you have process A running on CPU 0 and it accesses some data X on the memory 0. So it will take it less time for the process A to access X as compared to if it tries to access data Y on memory 3. Why? Because X is the local memory and it is connected with the CPU 0 with the fast bus. But if you now access memory 3, it is a remote memory, it will take much longer time because now you need to traverse this interconnect. And this is a simplified figure where you have only 4 nodes, right? But if you have more nodes, you will have your interconnect will be larger in size and will take even more time. The latency will be increased to access a remote memory depending upon where your data is located, right? So a process will experience low latency accessing local memory, but the downside is that if a process tries to access the remote memory, it will experience high latency, right? So then what is the solution? Solution mean like, yes, we are good when we are accessing the local memory, but we need to pay the high latency when we are accessing the remote memory. So how can we tackle or how we can address this problem? Like how we can reduce the latency when we are trying to run an application on the NUMA architecture. Someone said, can we not just have a main memory that connect all the locals? Can we not just have a main memory that connect all the locals? I don't understand what do you exactly mean. Can you please explain? You can unmute yourself and talk. Okay. Maybe you are not comfortable with explaining, so I will try to understand and then try to answer. Can we not just have a main memory that connect all locals? So if they connect all the locals, so again, like for example, are you saying, sorry, I meant to ask, instead of traveling through all the locals, can we connect all the locals to a main memory? So by all locals, are you saying connecting all the locals to the main memory? So which basically mean it can mean different things depending upon what you have in your mind. So let me just try to understand what you are saying. Are you saying like you have here a memory chip and then you somehow connect this memory 0, memory 1, memory 2, and memory 3 here, right? So if that is what you are saying, then let's say how it will solve the problem. Let's say I have process A running on CPU 0 and it want to access the data located at Y, right? Then how it solves the problem? Are you saying that Y first need to be moved into this central memory and then from here it can be accessed by process A, and from Y to this local memory 0, and then it can be accessed by A, but it will simply increase more, it will simply increase the time because now you are doing extra movement of the data. You are moving it from memory 3 into this central memory, then from here to the local, and then from local CPU accesses it. So it will only make the problem worse instead of solving the problem. Because just a simple rule is that more you need to do, the more you perform the data movements, more time it takes. Okay, so the solution for this kind of problem is that we need to have NUMA aware data placement. What does it mean? Again, let me just discard all the annotations. So remember, the problem was like, if I'm accessing a data which is not local, which is remote, then I need to pay high latency, right? So how can I solve it? By making sure that the data which I'm going to access, it is not placed in the remote memory. And how do I do that? I analyze my application and I look at the like data which is operated on by my application. And then what I do is that I place it in the, if I am running my application on CPU 0, then I place the data also in the memory 0. I do my best effort to avoid the placement of the data in the remote memory. Okay. This is a whole, like, this is just like basic idea. Otherwise, NUMA is a big and wide topic, right? So this is just, we just want here you to introduce to the terminology and very basic ideas, but we are not going to cover the NUMA here in full detail. Any questions? Okay. So until now, what we were doing was that we were first we were increasing the number of cores or the number of processors to increase the parallelism. Parallelism in the sense that we can run multiple tasks or multiple processes simultaneously. But then we find that if we keep increasing the number of processors or number of cores, then it becomes, after a certain point, it becomes expensive. Expensive in terms of power consumption, in terms of your cost, in terms of your latency, right? So then if that is the case, and then how can we increase the computing power even further, right? One solution was NUMA, right? But NUMA was basically, it was still talking about multiple processors in the same machine, and they have their local memories, and accessing the local memory is relatively fast as compared to accessing the remote memory. But the domain of your, like your thinking domain is same. You are still thinking in terms of processors on the same machine, on the same computer, right? So can we come up with a solution where we think beyond increasing the number of processors or core count? Remember, first what we did, we said, okay, increase the number of processors. Then we said increase the number of cores. But so we are going downward, right? Like from like upward processor, and inside the processor we have cores. So we said first we said increase number of processors, then we said increase number of cores in each processor. So instead of going downward, maybe we can go upward. Upward mean like we can say, okay, instead of like increasing the number of processors in the machine, increase the total number of machines, right? So what about parallelism at a level of a complete computer system rather than on level of cores or processors? So this is known as a clustered system. So it is like multiprocessor systems, but what we do is that we have multiple computer systems which work together as an integrated computing resource. Like they have we have a mechanism which give us an illusion that these multiple computer systems are logically a single entity. Okay. So actually we are combining the computing power of multiple computer systems together. And this picture is actually how to say, shows architecture of a clustered system. So in the cluster system, you have multiple nodes. So this is a single node, which is consisted of at the bottom, consisted of network interface, hardware. So it is a communication processor, which is responsible for transmitting and receiving data packets between nodes of the same cluster. And then you, on top of it, you have communication software, which is responsible for communication between nodes and the outside world. And on the and then here on the top you have the PCI workstation. And then there is a layer, a cluster, which is named cluster middleware, which actually its job is to offer an illusion of unified system image. So to the user, it looks like, just like, for example, when you are programming on your machine, like laptop or your desktop, doesn't matter. If you are programming in a higher level language, you don't care about the internal architecture of the processor in your machine, right? So it makes your life easier. Similarly, cluster middleware, it is software which actually makes life easier for the users of a clustered system by giving them an illusion that the cluster which they are working with is actually a single computing resource. And keep in mind that on cluster systems, you can run both kind of applications. You can run sequential applications and parallel applications as well. But we are not going to talk about parallel programming and related topics in this course. So like if you want to run parallel application and you have a clustered system, so what you can do is, like, parallel applications are those which can be, their like components can be run on different nodes at the same time. So if you can run their different components on different nodes at the same time, you can speed up their execution. But then the applications need to be written by following the parallel programming rules or concepts. Any questions? Okay, let me check the time. Yeah, we still have 15 minutes. So, operating system, how it operates. So first thing is, like, the question we are trying to ask is, like, how operating system responds to the different kind of events or requests happening during the execution of a process, right? So first thing we need to know is that operating system is an event-driven system, and it serves a running process based on events. So actually what happens is that if you have a process running in your computer, it generates events, and there are different kind of events. So if your process is not generating any event, it is saying that I don't need to interact with the operating system, or I don't need any kind of interaction or any kind of services from the operating system. So operating system will not respond to it, right? once the process is launched. I'm talking about that, like if it is only executing, let's say, user level code, right? So what are the events which can be possibly generated during the execution of a process? So there are three different types of events: fault, trap, and interrupt. Remember, we have talked about little bit about interrupts in one of the previous lectures. So let's first talk about faults. So faults, they are unintentional. Unintentional mean that it is a kind of event which is not generated on purpose during the execution of the process. So it is a event which occur, for example, as due to an error, right? So for example, when you are writing you wrote your program and you are doing some division, and the denominator of that division, its value becomes equal to 0 because of some mathematical calculation during the execution of the program, or maybe it is divided by the absolute 0, like a constant 0, right? So if that is kind of, let's say, an instruction in your program, so when it executes, it will result in a fault. But then no one intentionally want to divide something by 0 on purpose. So it is an unintentional happening or an unintentional event. The timing is like, it tells you about when does this event happens. So this event will appear before the completion of instruction execution. So your software or your operating system will detect it before the completion of the, it will be detected before the completion of the instruction execution, and then your operating system will be notified. So your hardware will actually not allow this kind of instruction to complete, and it will notify your like operating system by raising a fault type of event. Trap, it is intentional, and it appears after the completion of instruction. Actually, you intentionally in your program, you can put the instructions which result in trap, or which result in occurring of an event of type trap. So for example, if you want to debug your program, so let's say let me again draw something. So let's say you have a bunch of instructions, and then you put a breakpoint so in your program. So what happens is that these three instructions will be executed, and when you reach at the breakpoint, after the execution of the breakpoint instruction, a trap type of event will happen, or it will occur, and as a result, but it will happen after the completion of this trap instruction, this breakpoint instruction, and then your operating system will be notified, and then it will handle the trap by running some kind of routine, just like interrupts. Interrupts, they are external event. They are outside of the CPU pipeline, like for example, due to some IO device. And examples are like keyboard press or timer expires, and they can occur between instructions. Like this happens before completion of the instruction, this happens after the completion of instruction, and this can happen between any two instructions. Remember when we talked about it when we were discussing interrupts in previous lecture. Again, I need to get rid of the. Okay, so let's say if you have let's say you have OS code or kernel code, then it will be consisted of different kind of handlers. For example, interrupt handlers. So as I said, hardware or components outside your CPU pipeline, they cause an interrupt. And if an interrupt arises, then interrupt service routine will be executed, which is a component of OS. If a software error, for example, division by 0 happens, then what happens that a fault or exception will be raised, and then a fault or exception handle will be run by the OS to take care of that fault. Similarly, if a system request causes system call handle to run. For example, if you are like, let's say, I don't know, I mean, we will talk about it in, I guess, today's slide. If your program is making a system call, then your system call routines, which are also the component of the OS code, they will be invoked to take care of that system call. And then other than that, there will be other routines also in your OS code. So what we are saying is that in this slide, what is the main takeaway of this slide is that your OS is an event-driven software. So what happens is that your program, user program, or your process, when it is running, it may generate different type of events, like in category of fault, trap, or interrupt, or making the system call. And depending upon the type of the event, you will one of the handler routines will be run, like interrupt handler or fault handler or system call routines and so on. Okay. Any questions? Okay. So we talked about, like, if a process is running if a single process is running in your machine, which has an operating system, how then this operating system reacts to the events generated by the process, right? Now, let me check the time. Okay, we still have time. So now let's consider the situation where we want to run multiple programs on the same machine, right? So we have talked about like, okay, we need to have multiple cores, or we need to have multiple processors to run multiple programs or multiple processes, right? By the way, in this slide, job, process, running program, all of these terms will be used interchangeably, which basically mean that all of them mean the same thing. So why we want to run the multiple programs, like, even to start with, why we even want to run multiple programs, why we are not fine with running only single program? Because if we have single program, a single user, it may not keep our CPU and our devices busy all the time, right? So which basically mean, like, if I say that again, let me draw. So let's say if I have let's say this is CPU, and I have 3 processes, and this is like, let's say it's execution time, right? How long it takes for A to complete. And this is like for B, and let's say this is how long it takes for B to complete. And let's say this is C, and this is how long it takes for C to complete, right? Oh, sorry. Oh, it's okay. So let's say I first run A on the CPU, right? But then when a process is running, it is not like it is doing compute all the time. It is not like doing computation all the time. Maybe it will do computation, some computation, and then it will try to read some data from the IO devices, or try to write something to the memory or to the disk. And then after that, it will again do some computation, and then again write to some IO device or memory, and then again do some computation. So basically what I'm saying, like, let's say here we have some compute, and then here you have I'm putting this cross to just to indicate that here this process wants to do some IO or access the memory, and after that it again does some compute here, and again it does perform some accesses to IO devices, right? Now the thing is, like, when you are when the process is doing some computation, then it is actively using the CPU. So this is good. So when you are doing computation, you are actively using CPU. CPU is not idle. It is not wasted. But when computation is done and then it is time to perform some IO operation, then CPU is not doing nothing. It only is waiting for the process A, the IO operation requested by process A to be completed. So here in this area, it is staying idle, right? And then once it is done, then it may be start doing again some computation, which means that CPU is actively used. And then again, when IO is performed, then what happens that your CPU again waiting. Now, if I say that I will first allocate CPU to A and process A once it is completed, which means that all of this is done. After that, I will allocate CPU to the process B. Then it's mean that I am wasting this time here. I'm wasting this time, right? So it basically means that when I am allocating CPU to A, process A, it cannot keep CPU and IO devices busy all the time, because when it is doing compute, CPU is busy and IO devices are idle. When process A is doing IO operation, then IO devices are busy and CPU is idle, right? So at that time, I'm wasting CPU, right? So that is not a good idea. Anyone who has a question or some comment at this point? Everyone is with me on, everyone understand what I mean by single user cannot always keep CPU and IO devices busy? Okay. So what we do is that we want to run multiple processes on a CPU, even if we have a single CPU, right? Because we don't want that CPU to stay idle, because maybe a process which is running on the CPU is actually now doing IO operation and CPU is wasted, right? So what we do is that we keep a subset of total jobs in system in memory. So actually jobs are actually basically our programs, right? So first we load them, those programs from our storage into the main memory, same main memory where our operating system is also residing, right? So now we have multiple processes which use the memory at the same time. Now we need to do the memory management among them, but we will not talk about that right now. We will cover that later in week 10 to 13, memory management, right? So what we do is now, since we don't want to waste our CPU, or we don't want to waste our IO resources because we want to keep CPU busy all the time, and we want IO devices also the busy all the time, as long as there is work to do, right? So what we do is that we select one job or one process and run it via job scheduling or CPU scheduling, which we'll talk about later. So we select one of these three, let's say one of these three jobs, and allocate them to the CPU at a given time. And when we see that, okay, let's say we allocate job A, we allocate CPU to the job A, but then let's say job A performs, or process A performs some computation and then waits for IO. Now, when it is waiting for IO to complete, what we do is that we allocate the CPU to the job B, so that CPU is not idle. Now, what happens, the good thing is that process A is doing the IO operation and process B is doing its compute part of its execution. Now CPU is not wasted, IO devices are also not wasted, right? So when multiple processes are ready to run, they need to be scheduled for execution. Now let's say if process A was, as I said, let's get a step back. Process A was doing compute and then it started doing the IO operation. Now let's say B and C both are ready to run. So we will select one of them, either B or C. But how? On base of what criteria? This is known as CPU scheduling, and we will talk about that, like on base of what criteria we select the candidates, like whether B should be allocated CPU or C should be allocated. We will talk about it later. Okay. So this is known as multi-programming. We have single CPU, but we interleave different processes on the CPU to make maximum usage of CPU and IO devices. Okay, so this is the basic idea of multi-programming. Any questions? No? Okay, if no questions, then let's stop here. And we are kind of slow. We are falling behind from our tentative schedule, but we can try to speed up in next week. Okay, so let's stop here and then we can continue in the next lecture.